Return addresses, these are more difficult to find, so there's typical buffer overflow things, issues. GS is now enabled by default for the Windows driver kit. That doesn't mitigate all issues. GDI for the functions that pass up data to the display driver. If the buffers are smaller than 64 bytes for draw escape or 32 bytes each for ext escape, are just allocated on the kernel stack, both the input and the onboard buffer. So if data length isn't being validated in the kernel, there is the possibility of the display driver then overwriting the stack address for Win32k, and that is not protected by GS, by stack cookies. You can overwrite code from a kernel module. I don't know for sure whether it's the case on all versions of NT, but I've looked at SP2 and Vista, and kernel memory is writable by default. The I/O access map from the task state segment. This controls access to the instructions in and out. So if you can overwrite that, find that and overwrite it, then that will allow you to use the privileged instructions in and out, which can be used to interact with hardware. Also, any kernel structures. I have a demo later on which will find the process token for the parent process of and modify that in memory, changing the process pointer to the process token. That's elevating the parent process from unprivileged user, in this case, to operating system. The loaded module list, if you're writing a rootkit, or another example, the LUIDs used to define the actual privilege values. So SUDB privilege or SUTCB privilege are just internally numbers. If you find that table and overwrite that with values that is just a privilege that's available to all unprivileged user mode processes, then all unprivileged user mode processes all of a sudden have all privileges. So, real-world examples. These are all bugs I found recently. The kernel runtime library exports functions to support compression, LZ compression in the kernel. This is used by server message block code and NTFS for file and folder encryption. Internally, it takes a parameter that indicates what particular version of what particular flavor of compression to use. Only LZ is supported, though it was designed to be extensible. This is used as an index into a function table. There are only 8 entries provided. However, the maximum value allowed is 15. So obviously there are 8 other entries that are undefined. And depending how the compiler actually builds the executable, maybe code or maybe data. And those, whatever's there, may point into user mode and can therefore be trivially exploited. The issue with this is NTFS. The only way to access it is actually through NTFS, and that means modifying NTFS metadata directly on the disk. And to do that, you need to be admin or have physical access and a USB key, and that's not really a security issue. That's the exploitable code, as you can see. It masks it with it checks this 15 and then uses that as an index into this jump table, and these can be treated as pointers by the kernel mode code, and several of those are into user mode addresses. This is on disassembly from the Vista x64 kernel. All the bugs that I'm going to talk about have a greater deal of explanation in the paper. Following code is an example of a typical kernel mode issue. It takes a pointer from a buffer and just trusts it. The original version of the code I found this issue in either sign extended a stack address and then wrote it back to the pointer you supplied it, or wrote an internal handle there. The most recent versions I've checked just write the handle. So obviously some issue has been noticed there by the developers, but not addressed completely. This can be used to overwrite other code or data and allow arbitrary code execution. Key point being here, any pointers from user mode should be validated or should be treated as opaque, such as the handles the kernel itself uses for files, which are internally treated as indices into a handle table, but are not actually treated as direct pointers. I do actually have a proof of concept for this, which I'll go through briefly. If I could type. Yeah, so I'm a standard user. As it happens, that user is actually admin, but this will work with an unprivileged user. Sure. Well, I could do that bit. Probably change the font. There you go. So, standard user, well, admin user. This will exploit an actual bug for a driver that on a hardware on a system, which is why I'm not running this in a VM, because VMware doesn't currently support emulation of actual hardware beyond the processor, so you can't do things like I'm running a system, as I said. This just swapped the pointers to the process token in the eProcess structure in the kernel. And now this command prompt is running a system, so I have access to resources that the system process does, which is everything. This is the actual exploitable code in a modified form because it's as yet unpatched. This is where the sign extended stack address is written back to the user mode control pointer, which is in ECX. So it writes to ECX and ECX plus 4. Where the handle is written is not in this particular piece of code, but which is the actual vector for the exploit in this case. Trivial to find. This is more of an architectural issue. As I said earlier, there are sometimes some specific functionalities exposed to user mode which shouldn't be, or should only be exposed to privileged users. This is an arbitrary memory copy. In this case, fuzzing wouldn't have been much help, though it's just exposed by the I/O control interface. The structures that are passed into the kernel are quite complicated. There are several substructures, and it's unlikely to be hit in a meaningful way by a fuzzer. In this case, either access control to the driver, so as I said, a TCP privilege, or a different architecture is needed. And very typical stuff. It processes the data, gets pointers, and then right down here, it just does an optimized copy from user mode specified address to a user mode specified address. So how can we deal with these particular types of issues? First of all, as I said, parameter validation. This is an issue based on the documentation Microsoft provide now in the WDK that obviously Microsoft are aware of, based on my experience of driver code and device driver writers, not necessarily as widely appreciated as it needs to be. Code signing, as I said, Microsoft have introduced mandatory code signing for Vista. However, there is a question whether this code signing necessarily enforces code quality. And also, there are issues related to revocation. I don't know if anyone here has noticed, but last week someone released a tool on rootkit.com which had a signed driver, which then would load a user-specified unsigned driver into the kernel, thus bypassing the code signing quality. How do Microsoft deal with this? There is revocation. They can now revoke code signing certificates, but when do they do this? Do they do this every Patch Tuesday, allowing the stolen certificate to be used for a month, possibly, to assign rootkit drivers, or do they do it as soon as possible and push it out through Windows Update? PatchGuard. PatchGuard is another system introduced to try and a lot of people have looked at this from a security point of view as if this was in some way dealing with rootkits or malware in the kernel. I personally don't see it as that. It's a case of Microsoft trying to take control of the kernel, so they have more control over what goes in and therefore can have better control over the stability of the operating system and other security-related issues. PatchGuard has been fairly thoroughly discussed on uninformed.org. There's very good paper, well, two very good papers on there if you want further material. However, not all possible kernel mode structures are protected by PatchGuard. As I mentioned earlier, the objects in the object directory in the kernel all have function pointers. Those aren't protected. So it is still possible, well, quite trivial, to implement a rootkit that can hook the NDIS driver or the file system driver or any file system filter drivers and redirect the output and modify the output arbitrarily. Therefore, so you can still do network stealthing and exfiltration and file system filtering. Process manipulation is more difficult because those are implemented still by system calls. But it's not the thorough overarching solution to preventing PatchGuard in the NT kernel. As I mentioned earlier, Microsoft have moved some of the functionality in the kernel in Vista to user mode. So they've created a user mode driver framework, which is used typically for USB drivers, which provides a standard interface. So the actual third-party driver runs entirely in user mode and just accesses the services provided by the driver, thus reducing the amount of third-party code running in the kernel. Obviously, this has also been done with one of the components for the display drivers in Vista, and some of the actual internal Windows architecture has been moved from the kernel as well. You can restrict access to APIs as well, so based on the user, their privilege level, or privilege restrictions and process restrictions if need be. But that's only with the current architecture. And as I said, the design architectural solutions created in the 60s don't necessarily address the typical security problems that are faced nowadays. And it's awkward to backport the security into them. So there are alternative approaches. A lot of work has been done recently with virtualization and hypervisor. This has typically been done with rootkit work. There's talk after this, which is, I believe, related. Designed to help virtualization on a processor, so you can run different isolated operating systems on the same chip. Provides a layer beneath or above, depending on how you want to think about it, the supervisor of the operating system itself. And it could be used, in essence, to provide a microkernel architecture, so running the operating system underneath as less privileged, and then controlling that within the supervisor. However, that's quite difficult to implement, and a microkernel could just be used in itself. Microkernel